continuation from where we stopped. We said when it comes to shear force and bending moment diagram, we are doing strength of material, right? We are doing strength of material, and we look at the definition of strength of material. What does strength of material means? We said strength of material is just like we saying, just like as the name implies, strength of material. A body is subjected on a material. What is the limited magnitude that this body can resist, right? We've discussed all that previously. Now, also, if you're in the last class, I want to believe every one of us here, we already have the idea on how to draw shear force and bending moment diagram, right? True of us. Every one of us here, we already have the idea on how to draw shear force and bending moment. Is that not? So I want to believe that. So meaning that for today's class, it's going to be an interactive section. Today's class is going to be an interactive section. Now, when we started this particular course, this particular topic, which is shear force and bending moment diagram, I said there's one secret to this topic as far as strength of material is concerned. And the secret is that your steps remain the same. Your steps remain the same. Meaning that given a question, and you are able to solve that question yourself from step 1 up to the last step, nothing is changing. That's the meaning, nothing is changing. All right, now looking at this beam, I said for our level, given any type of beam in the exam, in the text, you'll be given only statically determinate beam, right? And I believe you know what statically determinate beam means. Okay, let me ask that simple question. What does statically determinate beam means? It means what? Equation of equilibrium are sufficient to analyze them. Now, first thing first, it works for every other question. First thing first, your first task is to identify. Ask yourself, what type of beam are you giving? What type of load are you giving? Now, let's do this together. Solution. You already have it in mind that I'm considering these 3 equations just because, okay, now this is it. Now, identify. What type of beam is this? What type of beam is this? You are correct. What type of beam is this? It is an overhanging beam. Yeah, if you say statically determinate, if you say overhanging beam, both of you are correct, right? But this, how to approach it, when I say that what type of beam is this, the answer should be what? Overhanging beam. Are you getting me? Your answer should be what? An overhanging beam. Now for the last time, what type of beam is this? An overhanging beam, right? And by overhanging beam, it means equation of equilibrium are sufficient to analyze them. That is, as far as this question is concerned, I'm making use of these 3 equations. Summation f of y equals 0, summation f of x equals 0, and summation of moment about any point equals 0. And we discussed, or we've seen the concept behind these 3 equations. We said that each equations, they have what? Sign convention, right? Each equation has sign convention. For this first one, this is the sign convention, right? Meaning force of this nature positive, force of this nature negative. Any question on that? The next one, this is the sign convention positive, negative. Then lastly, either you go clockwise or what? Anti-clockwise. This is your clockwise, and this is your what? Anti-clockwise. So every one of us here, I want to believe you already understood all of this. So this is what we'll be implementing basically, right? Now from here, first thing first, we've identified that this given beam, this is an overhanging beam, right? Now identify what types of load do you have? I'm having a U.D.L and I'm having a what? Point load. Now the question is, how many U.D.L am I having and how many point load am I having? 2 point load and 1 U.D.L, right? Now solution. I said I want an interactive class, right? This is the first equation of equilibrium, second equation of equilibrium, and third equation of equilibrium. So out of this equation of equilibrium, which one am I considering first? Out of these equations of equilibrium, which one am I considering first? Is it 1, is it 2, is it 3? It is 1, it is 1, meaning probably those of you that said 3, you're not in the last class. It is what? 1. You are considering this first one. That's your first equation. out of this equation of equilibrium. So if considering that, meaning summation f of y equals to what? 0. Force of this nature positive, force of this nature negative. Now go back to your beam, identify how many force of this nature do you have and how many force of this nature do you have. Considering your load, okay, this is it. Let's do it this way. How many forces do you have in general, how many forces do you have? Consider your load and your support as forces, right? It's just all about you looking at this beam given, then anything you are seeing, that's what you just be saying. Are you getting me? Nothing is hard. It is what you are seeing that you are saying. Now looking at this beam, how many forces do you have there in general? 5. I'm having 2 supports at A, at B, and I'm having a load, and I'm having a UDL and this 2-point load, right? Now you observe that each load has their respective distance, though it is only this CDL that has a distance. You know, your UDL, it is spanning from A to C. It is covering what distance? 4 meter. It is covering what? 4 meter. Now we've identified that I'm having 5 forces. I'm having 5 forces, right? I'm having 5 forces. Now the question is, how many force of this nature do you have and how many force of this nature do you have? Force of this nature, how many are they? 2. What about this? 3, right? I'm having this and this being force of this nature, and I'm having these 2 also with my what? UDL. I believe you know how UDL works. You can convert a UDL to a what? Point load. Now by doing so, now let's do this together. Meaning I have RAY, right, plus RBY. I want us to do this together, please. RAY plus RBY minus, we said force of this nature, they are considered positive, meaning this guy and this guy positive. All right, from here I'm having a support at A, it becomes what? RAY, right? I'm having a support at B, it becomes what? RBY. What if I'm having a support at D? What do we have? RDY. We are having what? RDY. Alright, now from here, meaning that force of this nature, they are just what? RAY and what? RBY. So we've written that. Next up, I'm having force of this nature, right? Identify how many are they? This guy, and this last guy, right? Meaning, we said force of this nature, they are considered what? Negative. Why are they considered negative? Just because they are acting downward. Are you getting me? So let's, depending on how you want to take it, you might decide to take your point load, then lastly your UDL. It is your choice, right? You are the one solving the question. All right, now how do you want it to go? Call it for me. Point load first. Tell me the value of the point load you are considering. Minus 20, minus 25, minus. All right, you are saying minus 10 from this end. You guys are agreeing with that. Minus 10. Minus what? Minus 100. Okay, 10 times 10 is 3. For the last time, minus what? Minus. Okay, that's correct. 10 times 4, 40. You are correct. Who can tell me the reason why we said minus 10 times 4 and not minus 10? We converted a UDL to a point load. Why are we doing that? Why are we doing that? Because any load subjected on your beam must act at right angle to the axis of that beam. Now mathematically, this guy, is he acting at right angle to the axis? No, meaning you have to convert. Just bear it in mind that when it comes to UDL, any type of load except point load, you are doing conversion. We've done all this previously. All right, meaning I'm having what? 10 times 4. Then what do I have again? Equals to what? 0. Because I'm done with all the forces, right? Now let's do this. Simplifying this, it becomes what? RAY plus RBY, right? Equals to 20 plus 25 plus 40. Therefore, RAY plus RBY is equals to what? 85 kilonewton. Call this equation 1. Call this equation 1. By equation 1, what does it mean? It means out of these conditions of equilibrium, we've implemented this first one, right? The next one is what? Summation f of x equals to what? 0. Now, the question you need to ask yourself is that, am I having force of this nature in the given beam? No. Who can tell me why? Who can tell me why? Just because giving the beam, I'm giving this beam directly, no stress. You know, we said we have support. By support, draw the free body diagram. You drawing the free body diagram, you are showing the yielding force. What if I have, let's say from the question, I'm having a pin support. Okay, let's say from here, I'm having a pin support. This is my pin support, right? By free body diagram, it means I'm having both vertical and what? And horizontal. Now, when it comes to this next equation, then you consider this guy true or false. True. But in this case, the question comes directly, no stress. Meaning there's no need of you start drawing free body diagram. So what it means is that for this next equation, do I still need to consider it? No. And the reason is because I'm not having force of this nature acting on my what? Beam. Right? Moving on, what's your next equation? Summation of moment about any point equals to what? 0. Summation of moment about any point equals to what? 0. Now, how many points do you have? You know, we said summation of moment about any point. When we say any point, what does it mean? How many points do I have here? How many points? I'm having 5. A is a point, C is a point, D is a point, B is a point, E is also a point. Now, when we say summation of moment about any point, does that mean we can take moment about C? We can take moment about D? We can take moment about E? Yes. Can we? Yes. No or yes? If it is no, why? Why is it no? Because no reaction. That's it, no reaction. The idea of moment is that just like the way you are doing your mathematics, say you have equation 1, equation 2, you must know a particular variable. You must know equation 1, then substitute to equation 2, right, to get the two unknowns. You taking moment at either of the support reaction. It means the support reaction at that particular point, you want to what? Eliminate it. You are eliminating it. That's the logic behind it. Now, from equation 1, I'm having two unknowns, which are what? RAY and RBY. So to get these two values, I have to know a particular value, either RAY or RBY. Once I've gotten the value, then substitute back to this equation 1. Now, say you are taking moment about point A. What does it mean? RAY has been what? Eliminated. Then you'll be able to get this very guy, right? Vice versa. If you are taking moment about what? B. Now, taking moment about any point. Taking moment about any point. I said it. Emphasis on it. It's always attract mark. Some lecturer in this our school, they are very, very, very strict. When I say strict, 100% strict when it comes to marking. So when taking moment, it does not mean you don't know what you are doing. You know what you are doing, but they will believe you still don't know what you are doing. That's it. Now you have to write it. Taking moment about whatsoever point, you are taking the moment. Now for this class, or for this given question, what point should we take the moment to? A is your choice. I've always said that it is your choice. You can take moment to A or you take moment towards B. The only thing is that understand the what principle. Understand the principle. So for the last time, at what point should we take our moments? A or B? A. All right. I would have loved us taking moments about point B. Do you know why? Because when you want to consider this U.D.L, you would have seen how it works. But regardless, when we start bending moment calculation, you still see the concept. Don't worry. So you guys are saying I should take moments about point A. Now the idea is that if you are taking moments about point A, it becomes less complicated. If you are taking moments about point B, it becomes what? Complicated. They are still the same thing. What's that? You should take moment about B. Yes. All right. Let's take moment about B. Let's take moment about B. All right, let's take moment about B. Right, taking movement. Hope you guys are following me with these steps in your notes. Right, taking movement about point C. They've not gotten to the interesting part yet. Sorry, point B. Taking movement. Taking movement about point B, right? Then mathematically, what do you have? Summation of movement about point B equals to 0. Now you know how movement works, right? By definition, what is movement? By definition, what is movement? Movement simply means the product of the force times the perpendicular distance to the turning point. I said, what does movement mean? Movement simply means what? The product of force times the what? Perpendicular distance. Now, from here, I'm taking my movement to point B, right? So what it means is that, earlier, initially, when we identify the total force we are having on this beam, how many are there in total? There are 5, right? Just because I'm taking moment at point B, what does it mean? The particular force on B, which is RBY, has been what? Eliminated. Meaning, how many forces are you left with? 4. So what that means is that the remaining forces, they are traveling towards B. Are you getting me? The remaining forces are traveling towards B. Meaning that the force on A, which is RA1, is going to be, this particular U.D.L is going to be 25 kilonewton is going to be, and lastly this 20 kilonewton is going to be. So irrespective of the way you are taking your movement, you still get the same thing. But for me, when solving this shear force and bending moment diagram, I always love going gradually. Are you getting me? When I say gradually, meaning I'm starting from 0 up to the last span of the what? Beam. Now looking at this beam, what's the total span? When I say span, I mean length. What's the total span? 7 meter, right? 7 meter. So when I say gradually, so the total length of this beam is either you call it length or you call it span. So the total span of this beam is 7 meter. So me taking my movement, or in any calculation, if it is shear force calculation, bending moment calculation, I always love going in a gradual process, meaning that I'm starting from 0 towards 7. Now going in that order, meaning respectively, the forces I'll be seeing, I'll be taking their movement towards point B. Now let's identify, going in a gradual process, what will be the first force that I'm going to see? RAY. Because A is the starting point, meaning the first force I'm considering is what? RAY. So what it means is that RAY is going towards B, right? By movement, we are saying that movement is equals to force times distance. Now from here, RAY is your force, right? Now ask yourself, this RAY, what's the distance RAY is covering to get to point B? Before getting to B, 6 meter, right? Meaning the movement for this force at A simply means what? It means what? RAY times 6. But the question is that this force, which is RAY, is it going in a clockwise direction or anti-clockwise direction? Clockwise. Why is it clockwise? I can see some people doing like this now. Clockwise. We simplify this. I know this is the technical part of shear force and bending moment. Very, very technical. So I simplify this to a level whereby you can grasp it, you can get it. Right? Meaning, I drew a wall clock using that as an analogy to explain the concept behind clockwise and what anti-clockwise. So, if you are in the last class, check your notes. What part is this A traveling? Is it 1? Is it 2? Is it 3? Is it 4? 1. It is going in that order, right? By 1, is it clockwise or anti-clockwise? Clockwise. Meaning you are going in this manner, you are traveling like this up towards B. Just imagine it as you tipping the arrow of RAY, you tipping it, you will notice that you are going in the direction of your work clock. You going in the direction of your work clock, it becomes what? Clockwise. You going against it, what do you have? Anti-clockwise. Then by when we say going in the direction, positive or negative? Positive, meaning I'm having what? Positive RAY times what? 6, right? Next up, I've considered, don't forget, you are going gradually. Me going gradually, I'm starting from 0. I've considered this force, right? Yeah. The next force that I'm saying is what? Yeah. A UDL. A UDL. By UDL, I need the force of this UDL, right? Yeah. And I also need what? Distance of this UDL. Now, what will be the force of this UDL? 40. How do you get 40? 10 times 4. You already know that. What about the distance? How do you get the distance? Now, understand the question. Understand the question. My question for you guys is that what is the distance of this UDL? 2. That's correct. The distance is what? 2. Taking the moment of this UDL to be, what's the distance? 4. How do you get 4? 2 plus 1 plus 1. If I ask you a question saying what is the distance of this UDL and you are telling me 4, you are wrong. Just because it's the questions are different. The first question is what is the distance of this UDL? The second one is what is the distance of this UDL where you are taking the moment to be? Are you getting me? Now, what is the distance of this UDL? 2, right? You know, we said moment means force times distance. I would have considered 2 being the distance, but I'm taking the moment of this UDL to be, meaning I have to consider the remaining distance before getting to B, which are what? 1 plus 1. So I have that. Now, the question now is, am I going in a clockwise direction or anti-clockwise? Anti-clockwise. Meaning I have negative, all into brackets, 10 times 4, all into brackets, 1 over 2 times 2, sorry, 1 over 2 times 4 plus 2. Plus 2. Alright, moving on. The next force you'll be seeing is what? 25 kilonewton. 25 kilonewton. Same idea. So this becomes what? The moment of 25 kilonewton becomes what? 25 times what? 1. Now ask yourself, is it going in a clockwise or anti-clockwise direction? Anti-clockwise. It then becomes what? Negative 25 times what? 1. Are we done with all the forces? No. Which force have we not considered? 20. Which force are we here to consider? 20, right? At E. Now, in what direction is 20 going? Clockwise or anti-clockwise? Clockwise, meaning I'm going in this manner. I'm going in this manner. So you going clockwise, what do you have? Positive 20 times what? 1. What else? That's all. Then equates to what? 0. So let's simplify this. Let's perform our algebra. It becomes what? 6RAY, right? Negative 40 times 4. What do you have? That's 160, right? 40 times. Yes. This is 40. 10 times 4 will give me what? 40. This will give us 4. Meaning 40 times 4. What do you have? 160. Negative 25 plus 20 equals to what? 0. 6RAY minus 160 minus 25 plus 20. The algebraic sum of this, what do I have? I have 165 over 6. Then by the time you divide both sides by 6, you end up having 27.5 kilonewton. So this is what? Equation 2. Alright, from equation 1, I'm having two unknowns, which are what? RAY and RBY. But in this case, I've gotten RAY, which is the first unknown. So I can substitute it back towards equation 1 so as to get the other unknown. By doing that, it becomes what? What do I have, guys? Please, come on, we have. What do I have? So I have, by substituting equation 2 into equation 1, I have 27.5 plus RBY equals to 85. Make RBY the subject of the formula. It becomes RBY equals to 85 minus 27.5, which is equals to what? 57.5 kilonewton. Alright, now I've gotten the value of the support reaction. Usually the question will say that find the value of the support reaction. That's just question 1A. So far we've calculated the support reaction values, which are what? RAY and RBY. The next step, from here, you've answered question 1A. Question 1B says that draw your shear force and bending moment diagram. And we said that before you can draw shear force and bending moment diagram, you need shear force value and you need bending moment value. So what that means is that I need to get shear force values. And how does it work? You simply get shear force value at each point on your beam, right? You simply get shear force value at each point on your beam. Earlier, we've identified that I'm having 5 points, right? Meaning at each point, I'll be getting shear force value and I'll be getting bending moment value. Based on our previous example we've seen how it works. So nothing is changing. That's what we are still implementing. But let's remind ourselves that shear force is calculated twice. I'm on a point. I want to get the value of shear force. I will calculate it twice. How do you get the first value? The algebraic sum behind the forces you want to calculate shear force, right? Then number 2, meaning what you've calculated, which is the algebraic sum, plus the force at that point. So that's what we'll be doing when it comes to shear force calculation. Alright, shear force calculation, right? Shear force calculation. By shear force calculation, we are saying that we are calculating the value of shear force at each point. And I always love going in a gradual process, or it is advisable to go in a gradual process. Meaning that if the total span of this beam is 7 meters, you going in a gradual process. What it means is that you are moving from 0 to 4, 0 to 5, 0 to 6, then lastly 0 to 7. Now, at A, what's the value of X? 0 meter. How do you get the first value of shear force? Please, let's do this together. You guys will be the one telling me what to do. So how do you get the first value? Alright, before then, let's substitute the value we've calculated. Our RAY, we got 27.5 kilonewton. Our RBY is what? 57.5 kilonewton. Alright, at A, X equals to 0 meter. What is the first value of shear force? How do you get 27.5? Okay, that's correct. 27.5 is correct. Why is it correct? It is what? Reaction at A. In this case, I want to consider the algebraic sum of forces behind A. But the question is, do I have any forces behind A? No. So say 0, right? And that's the first condition of shear force. Now, number 2 is telling you that the previous calculation you did plus the force on that point, meaning 0 plus the force on that point, which is what? A. Now in this case, what's the force on A? 27.5 kilonewton. Meaning at A, my shear force value is what? 27.5 kilonewton. Now the next point is what? At C, X equals to what? 4 meter. The first value of shear force, how do you get it? What forces are you considering so as to get the first value here? 2, which are what? This RAY and this U.D.L. By RAY, we are saying that RAY is going upward, U.D.L is acting downward. So it becomes what? 27.5 minus 10 times 4. So what do you have?
Minus 12.5.
Minus 12.5 kilonewton. Number 2 value of shear force. That becomes what? Can we get number 2 value of shear force here? Is second condition of shear force met at this point? No, just because we don't have a force at that point, right? We don't have a force at that point. So depending on you can still show it, but we don't really need to show it. So me showing it, I would say the previous force I've calculated, which is negative 12.5, plus the force on that point. I'm not having any force, so let's say 0. So I'm having what? 0. This is still what? Negative 12.5 kilonewton. Mind you, when plotting your graph, you take one of these two values. Now the next one is what? At D, x equals to what? 5 meter. Your shear force value becomes what? How many forces do you have behind? I'm at point D. I'm having 3 forces or 2 forces?
2 forces behind.
I'm having 2 forces behind, which is RAY and this CDL. So I still have, let's do that together. What do I have? Minus 12.5, still same value. But how do we get this value? 27.5 minus 40, which is equals to what? Minus 12.5 kilonewton. Alright, from here, this is just the first value of shear force at D. How do you get the second value? The second value of shear force at D, that will be what? Or can the second value be calculated at D?
Yes.
Why? Because there's a force on that point. So I have the previous one I've calculated, which is negative 12.5 plus the force on the point is what? 25. Sorry, minus 25. So this is what? Minus 37.5 kilonewton. Any shear force value at D again? No shear force value. Moving on to the next point. At B, what's the value of x? 4 plus 1 plus 1, what do I have? 6. 6 meter. So meaning the first value of shear force becomes what? How do I get the first value of shear force? That would be what? Minus 37.5. Minus 37.5. You can come back to your B. You have this RAY, this U.D.L, and this 25 kilonewton. You know, I said it before. The last value of a point will be the first value of the next point. Say this is A. The last value is what? 27 point. Okay, let's start from C. Say this is C. The last value is what? Minus 12.5. The next point, which is D, the first value will be what? Minus 12.5. Meaning that the first value in this case will be what? Minus 37.5, which is the last value here. But if truly you want to know if that's correct or if it works like that, come back to your B. I'm on point B. How many forces do you have behind? I'm having RAY, this U.D.L, and this force. Combining all of this, what do I have? I have 27.5 minus 40 minus 25, which is still what? Minus 37.5 kilonewton. The second value becomes what? Minus 37.5 plus 57.5. This is what? 20 kilonewton. The next point at E, what's the value of x? 7 meter. The first value of shear force becomes what? The last value here, meaning 20 kilonewton. Then second value is equals to 20 kilonewton minus 20 kilonewton, which is equals to what? 0. I'm on point E. 20 is acting downward. I have negative 20. The last value that I calculated here, positive 20. Any question? Alright, this is your shear force calculation, meaning shear force value at each point. The next one, bending moment calculation. Question 1 says that calculate the support reaction. We've done that, right? Now, draw the shear force and bending moment diagram. By shear force diagram, you need shear force value. We've done that also. Now, bending moment diagram. We need bending moment value. Bending moment diagram, we need bending moment value. So let's solve for bending moment at each point. So write bending moment calculation. The first point, just like the way you did for shear force. At A, x equals to what? 0 meter. In this case, bending moment must start with 0 and must what? End with 0. So now, your starting point, which is A, what's the value of bending moment? 0. Right? The next point at C, x is equals to what? 4 meter. What's the value of bending moment? What bending moment means is that What bending moment means is that identify the forces behind the point you want to calculate bending moment value. So I'm on point C. Behind C, I'm having two forces, meaning I'm taking the moment of these two forces to C. So the first one, what do I have? Let's do it together. What do I have?
27.5.
Clockwise or anti-clockwise?
Clockwise.
27.5 times 4 minus
40 times 2.
times 2, right?
Yeah.
This is the force and this is the what? Distance. This U.D.L convert it to force. 10 times 4. That's this. 40. The distance of this U.D.L is what? 2. So that's what we have here. The algebraic sum of all this, it becomes what? Are you sure about that?
Yes.
30 kilonewton meter. Bending moment, meaning force times distance. What do I have? 30 kilonewton meter. The next point at what? At D. What the value of X? 5 meter. Bending moment becomes what? 27.5 times 5 minus 10 times 4 all into bracket 3. How do you get 3? The distance of this U.D.L 2 plus I'm going to D, meaning before getting to D I have this additional one. It becomes what? It becomes 3, right? So are we done with the bending moment calculation at D? 25.7 times 5 in a clockwise direction, negative 10 times 40 if converted to a point load, then the distance 1/2 times 4, that's the force of this U.D.L. I'm going to D plus 1. So what is the algebraic sum of this? What do you have? What do you call it? 17.5 kilonewton meter. You can confirm this. 17.5 kilonewton meter. The next point is what? At B, what the value of X?
6 meters.
6 meter. X is equals to 6 meter. Now from here, bending moment value is what?
27.5 times 6.
Bending moment value is what?
27.5 times 6.
First thing first, identify how many forces do you have behind B? 3. Meaning these 3 forces, you are taking the moment to B. You are taking the moment of ROI to B, the moment of this U.D.L to B, and the moment of this 25 kilonewton to B. So let's take the first one, which is ROI. What do I have? In a clockwise direction, 27.5 times what? 6 minus your U.D.L. Your U.D.L, is it going in a clockwise or anti-clockwise direction? You have negative 10 times 4. This is just the force. The distance 1/2 times 4. Before getting to B plus what? 2. 1/2 times 4, the distance. Before getting to B, 1 plus 1 will give you what? 2. So what's the answer to this? You put this in your calculator. What's the answer? This will give you what? Minus 20 kilonewton meter. The next point at E, what's the value of X?
7 meters.
7 meter. Bending moment value becomes, without solving, 0. Without solving, 0. Just because we know that bending moment must end with 0. If it does not end with 0, you are doing rubbish. Just like the way we've seen that we did rubbish before. We did rubbish. So now, from here, just to show that, okay, I know what I'm doing, right? Let's write it out. That becomes what? 27.5 times 7. 27.5 times the total distance minus 10 times 4 minus 10 times 4 times 1/2 times 4 plus the remaining distance, the addition of 1, 1 and 1, meaning what? 3. So you have plus 3. Then this is just for your U.D.L. The next one is what? The next one is 25 kilonewton minus 25 times 2. All right. Next up, you have this support at B, meaning plus 57.5 times what? Times 1. All this must give you what? 0. Individually, what do we have? This is what? What's the value of this? What's the value of this? This one is what? 192.5. What about this? Minus what? 200 minus 50 plus 57.5. And this is equals to what? 0. This is equals to 0. Can you see what we are saying? Bending moment must start with 0 and bending moment must end with 0. Shear force, not necessarily shear force start with 0, but it is necessary, it must end with 0. Are you getting me? Now all this value that we've calculated so far, we want to plot it on a graph sheet. We want to what? Plot it on a graph sheet, and that's what shear force and bending moment diagram means. That's what it means. Calculating the value you've estimated from each point on your beam, plotting this value on a graph. Plotting this value on a graph. So let's do that. When drawing your diagram, if you started the class with us, I said something. Always what? Draw your diagram to scale. Even though you are using even though you are not using graph, always draw your diagram to what? Scale. By scale, meaning if you are having, in this case I'm having 4 meter and 1 meter. It is obvious that 4 meter is bigger than 1. So you draw your diagram. Don't draw your diagram saying 4 meter is lesser than 1. It is a minus for you. It is a what? Minus for you. Are you getting me? It is a minus for you. So what I'm saying is that draw your diagram to what? Scale. Some lecturers, even though I'm a lecturer, I'm going to do that. I'll minus your mark. So draw your diagram to scale. But I'll still be nice, anyways. For some lecturer, if you get everything, they'll still want to minus something. So that's it. Now from here, I'm having from A to C as 4 meter. Meaning, hello, in this case, pay attention now. I'm having span AC, span CD, DB, and BE. Meaning span AC will be greater than all these other lengths, right? Just because this is 4 and this is what? 1 meter. So my diagram, I'm saying I should have my diagram in this manner. Let's say I have this my diagram. This is A, right? This is C. I'm having a point load. I'm having a point load at B, right? Sorry, D. The next one is what? I'm having a support. Okay, this support is not here. The support is here, right? Then lastly, I'm having a point load. This diagram is still manageable, right? It is drawn to scale. So from here, this is A, this is B, this is A. Are we together? This is A, this is B, this is C, D, and lastly, what do we have? E. From here, let's load this our beam. Load your beam. This, what's the value here? This is what? 10 kilonewton. This is what? 25 kilonewton. What about this? 20 kilonewton. The distance here is this is 4 in length. This is what? This is 1 meter. This is 1 meter. This is also 1 meter. Right? Now from here, what's R1? And what's RB1? RB1 is what? 27.5 kilonewton. What's RB1? 57.5 kilonewton. What we are doing basically is that we are imagining that we are plotting this value on a what? Graph sheet. We are plotting this value on a graph sheet. I'll be doing a board diagram here, right? I'll be doing a board diagram. So meaning that since this is not a graph sheet, you'll be using your book for that too. So do something like this. Meaning we want to represent this sheet as graph. So do something like this. At each point, draw a vertical line. So you have this. So you have this, right? You have this. Do you know the reason why I said draw your diagram to scale? This shear force, let's relate shear force and bending moment to applied mechanics. What aspect are you going to refer it as? Is it under centroid? Is it under moment of inertia? Is it under equilibrium of forces? Is it under friction? Are you getting me? What are you going to relate it? Under what are you going to relate it? Equilibrium of forces. By the word equilibrium, what are we saying? Balance. Yeah. Meaning that you are illustrating the word equilibrium in a graph sheet. Are you with me? Meaning that you are illustrating the word equilibrium in a graph sheet. Are you getting me? Meaning that we are going to have a diagram here. You are also going to have a diagram here. By equilibrium, since this is 1 meter, this is 4 meter, this diagram must be smaller than this. Are you getting me? That's what we are saying. Now from here, just nothing is changing. Just know that nothing is changing. So we want to draw shear force diagram. Take a reference line. Both shear force diagram, take a reference line. Bending moment diagram, take a reference line. So for my shear force diagram, this will be my reference line. This should be my reference line. This is reference line, meaning origin 0, 0. So this is what 0. Now go back to shear force calculation. The value you've calculated at each point, that's what I need. The value you've calculated at each point, that's what I need. Or at point A, how many value do you have? 20 what? 27. Okay, now let's do this. Check the highest value of shear force. For shear force calculation, what's the highest value? 57.5. What do you call it? 57.5. 57.5. All right. So let's say I have, since the highest value is 57.5. So whatever thing I'm doing mathematically, I must maintain the range of 0 to 57.5. So let's say this is 0. Then I'm saying this is 57.5 kilonewton. This is the positive region of my graph, and this is the negative region of my graph. So let's say this is also 57.5 kilonewton. So what you are trying to say is that whatever value you be plotting must be within the range, either positive or negative, must be within the range of 0 to 57.5 in the upward region, and 0 to 57.5 in the what? Downward region. So, the other value of the shear force is 27.5. Are you sure about that? It's RA now. RA is 27. All right. Let's consider it as the highest value is 57.5. Just now the highest value, either for shear force or the support reaction. Watch out for the highest value. Just because 57.5 is going to push upward. You see it. Now from here at A, what value do I have at A? 27.5. So let's say I have 27.5 at this point. Are you getting me? So let's say I have 27.5 kilonewton at this point. Do you have a number greater than 27.5 again? No. Okay, if that be the case, let me extend this. Let's say I have it here. 27. Let's say I have, this is my RAY, 27.5 kilonewton. So let's say I have 27.5 at this point, right? Any value of shear force at A again? No value. Moving on, at C, how many value do you have? What do you call it? 27.5 and minus 12.5. Now, the correct one is minus 12.5. Do you know why? Are you sure we calculated shear force value? We got two value at C for shear force. Is it? We got the two value negative. Yes. No. There's no value there that is positive. No. Only 20 is positive. 20 and 27.5. Okay, what you are saying now is that at C we got two value. Yeah. What are these values? At C we got minus. Only one value. It is not possible. C we got minus 37. Exactly. At D you get 2. You can say that I know what I'm doing. Me looking at this, I know if you are telling me rubbish, I know. Just because I know the expected diagram I'm expecting for shear force. I know it. Say you have C, telling me you have two value. It means I'm having a value here. I'm having a value here. At the end, if you want to draw shear force diagram respectively, it becomes this to this, which is wrong for U.D.L. It is totally wrong. U.D.L must be slanted. Must be slanted. So that's it. So meaning that at C, how many value do I have? Just one, which is minus 12.5. So I'm saying, let's say we have minus 12.5 here, 12.5 kilonewton. Don't forget, this is my negative region, so it doesn't mean if I'm not showing the negative sign. All right, moving on to D. How many? Moving on to D. Moving on to D. What do you call it again? 12.5 kilonewton. Moving on to D. How many value do I have?
2.
And these are what?
12.5 and that's
So meaning 12.5 is also here. 12.5 kilonewton and what?
37.5.
What do you call it? 37.5. You know, initially, what do I have here? 27.5. 27.5. Wait. Okay, I'm having negative 12.5 and minus. Alright. So let's say I have 37.5 kilonewton. Always watch out for this. It must still be in the range of this. It must still be in the range. Just because this is a board diagram. And even I'm using graph, everything will be perfect. Alright. Any value again at D?
No.
What about B? Moving on to B.
Minus 20.
Positive.
20.
Is
And 37.5.
Exactly. Minus 37.5 before positive 20. So I'm having this 37.5 kilonewton. Then you cannot tell me positive 20. So by positive 20, if this is 27.5, it is going to be below it. So let's say this is 20, right? 20, right? 20 kilonewton. The next one, this is also 20, and this is 0. This is 20 kilonewton, and this is what? 0. Now, respectively, what did I say? I always make emphasis on this respectively. The way you assign the point on your graph, that's why it must touch each other. Also that you have this point, now taking from this, you are wrong. Just taking it anyhow, you are wrong. But respectively. So doing it respectively, I have this. The first one, tell me respectively, tell me the values I'll be meeting. Tell me the value I'll be seeing. From 0 to 27.5 to what? Negative 12.5 to negative 12.5.
So -37.5.
Negative 37.5. Negative 37.5.
Positive 20.
Positive 20.
Positive 20.
Positive 20. Shade. Yeah, not really, but shade. It makes your work neater.
Okay, then we are going to use
Positive, positive, negative. Right. Shear force diagram. Anyhow, just maximize your time. Just make it of your time. Now from here, let's take it back to what we've done previously. This is where I've been waiting for. You know, our first example was just a simply supported beam loaded with a point load. Our second example was just a simply supported beam loaded with U.D.L of different intensity. Now I said a point load has the pattern of shear force, right? Bending moment has the pattern of shear force, right? Are you getting me? While the pattern for point load shear force is always in square. You'll be seeing it in square. For U.D.L, slanted manner. Now I'm going up. A to C, what do I have? U.D.L, slant. On A, from 0, it is pushing it up. Why is it pushing it up? I'm having this support reaction. This is the magnitude. It is pushing it up. From A to C, I'm having a U.D.L, slant. Right? From C to D, I'm having a beam. A beam is still a line. Draw a line. On D, I'm having a point load. It is pushing it down. I'm having a line. I'm having a beam, draw a line. On B, I'm having a support reaction of magnitude 57.5 kilonewton. You know, from here, I have 37.5 kilonewton. Meaning 57.5 is going to push 37.5. You'll be left with what? 20. This is it. From here, I'm having a beam, draw a line. On getting to this point, I'm having a load. It is pushing it down, 0. Can you see how equilibrium has happened here, or it has occurred? you represented the word equilibrium graphically. So that's shear force. Now bending moment diagram. Bending moment diagram. Our next example, which I don't think is going to be today, probably Friday, is just because of what happened. If not, we'll have covered it. It is maximum bending moment, and point of contraflexion. But before that, looking at this beam, where do you have, okay, this is it. We've calculated at A, we've calculated bending moment. At C, we've calculated bending moment. At D, we've calculated bending moment. At B, we've calculated bending moment. At E, we've calculated bending moment. Now, the bending moment at C, what's the distance? 4 meter. The one at D, what's the distance? 5 meter. 5 meter. Back to A. The one at B, what's the distance? 6 meter. The one at E, what's the distance? 7 meter. Now, check the greatest value out of all this value of bending moment. In your calculation, check the greatest value. 30. At what distance does that occur? At C, meaning what? 5, meaning 4 meter. So, does it mean that at C, we can only get the greatest value of bending moment at C? No. The same way we take bending moment value at 4 meter, we can also do it at 4.5 meter. We can also do it at 5.5 meter. Any point that you can imagine, we can also do it there. Right? Yeah. So what maximum bending moment is saying is that at what point in this axis of the beam do you have the greatest value of bending moment? Meaning by calculation, that's not the actual greatest value of bending moment. Yeah. Are you getting me at all? Now, it is very easy. How do you identify? Where do you have your shear force changing sign? Where do you have your shear force changing sign? By changing sign, do you see reason why you need to shade? Where do you have it changing from positive to negative? Okay, let's do this. Let's say I have, call this A, B, C, D, E, F, G. Now, out of all this alphabetical representation, at what point is it changing sign? At B. At B. So because it is changing sign at B, whatever distance you have at B becomes the greatest value of bending moment for this beam. Meaning that greatest value of bending moment can only occur when X is lesser than 4. Do you agree with me? Yes. When X is what? Lesser than 4. But we don't know the precise value. Is it 3.5? Is it 3.6? Is it 3.7? Is it 3.8? We don't know. How do you know? You calculate. We have two methods. Okay. We have two methods. Observe. Back to what? Similar triangle. This is a triangle. This is also a triangle. Yes. You can use that method. Yes. You can use that method. Or simply section this beam. We've seen the idea of sectioning. Yes. Sectioning simply means you are separating that beam. Now, simply section your beam. The point where it's changed, trace it up, section it. By the time it's sectioned, I'm saying you have this. Right? You've sectioned, right? Yes. By the time it's sectioned, you have this beam left. Are you getting me? Yes. Now, take shear force. The shear force you've been doing, take shear force at this point. Take shear force at this point. You taking shear force at this point, it means from A to that point, X meter. That's X you want to know. So take shear force there, you get the value of X. Meaning any value you'll be getting becomes the value where maximum bending moment will occur. Where maximum bending moment will occur. Some question will now go further, calculate the value of this maximum bending moment. What you've calculated is only the location of maximum bending moment. Question will now go further and says that calculate the value, calculate the location and the value. You're not calculating the value, take moment at that point. Meaning the X value you've gotten, substitute it. Are you getting what I'm saying? Yes. So you have two methods. The first one is you considering that right angle triangle. The second method is section your beam and take shear force there. So we'll see that later. Section. But this is just shear force diagram. Let's draw bending moment diagram. Let's draw bending moment diagram. All right. So similarly, I took a reference line for my shear force, right? Same thing. Take a reference line for your bending moment. So by reference line, you are just taking a origin. So this is 0. This is also 0. Now, the same way we represented the shear force value on a graph sheet, you are also representing bending moment value on a graph sheet. So at A, what's the value of bending moment? 0. So you have this point. Any value aside from 0 again. Moving on to the next one, C, 30. What's the highest value first? 30. So let's say you have 30 here. What will be the unit in this case? 30 kilonewton meter. Any value again? No value. All right, moving on. At D, what do you have? 17.5. 17. Let's say this is 17.5 kilonewton. Kilonewton what? 17.5. This is the point. 17.5 kilonewton meter. Any value again? No value, right? So point B, what do we have? Minus 20. Minus 20. So let's say you have, I'm just managing my board. If you are doing your graphic, draw to scale. From here, this is my highest value, which is 30. The next point is what? 17.5. See the difference from the origin to 17.5. Observe the difference, right? Now I want to draw 20, or I want to pick the point for 20. It means 20 is going to range more than this one. Are you getting me? So the difference, we have the difference larger, right? So from here, if this is 17.5, let's say I have 20 kilonewton meter. Any value again?
No.
Then the next line, E, meaning 0. So what do? Respectively. By respectively, you are saying the way you indicate those values. So I want you to tell me how it works. From 0 to what? Is it from 0 to 17.5? To what? 30 to 30. Now you join your bending moment diagram. What is the expected curve? Parabolic. Just because U.D.L must be in parabolic nature. What about point load? Triangle. So let's say you are separating this span, this beam. This must give you a parabolic shape. This must give you a parabolic shape. And this must give you what? A triangle. So you combine the simply supported of a U.D.L and the simply supported of a point load, of a center concentrated point load, right? Are you getting me?
Yes.
So let's use that to understand. So meaning that if you are not given graph in your exam and you want to draw this line, don't draw something like this. You are wrong. You must have what? The nature must be what? Parabolic. The nature must be parabolic. So meaning I will try my possible best to have a parabolic what? Shape. So by that I have this. Right? 30 to what? All right. 20 to what? Any question? Is this correct?
Yes.
It is correct. Why is it correct? I'm having a parabolic nature for my U.D.L and this guy, triangle. Now shade as usual. I believe you should have seen the reason why you are shading now.
Yes.
Just because there's this particular point you want to indicate or want to identify. So shade your beam, shade your diagram as well. You shading your diagram, negative, positive, right, bending moment diagram. Same idea. Maximum bending moment and point of contraflexion, they are synonymous. The difference is that maximum bending moment, you identify it on shear force diagram. Point of contraflexion, you identify it on bending moment diagram. So with that being said, does point of contraflexion occur for this beam? Yes. Why? Because bending moment diagram changes from positive to negative, which is at this point. Which is at this point. So you've not solved now, right? You've not solved. But if the question now says that calculate the location where point of contraflexion occur, meaning that from this distance to this distance, say x meter, you must know what x is. You must know what x is. The difference is that for this one, the same way you section for this guy, you also section for this guy. But for this one, take shear force. We said maximum bending moment, you identify it on shear force diagram. Point of contraflexion, you identify it on bending moment diagram. This is a maximum bending moment, right? This is point of contraflexion. Now, we want to get the value of x. You know, this is the x for point of contraflexion, and this is the x for maximum bending moment. So now, as the name implies, you are going to section this beam as well. After sectioning for this guy, you'll be left with something like this, right? I've sectioned. This is, we don't know this point, say x meter. This is A, this is 10 kilonewton per meter. This is what R AY. The same way you section this also, you have another type of beam, right? Now, where do you section this beam from? Is it from shear force or from bending moment? Just because you've sectioned from shear force diagram, take shear force about this point, you get the value of x. Just because you've sectioned from bending moment diagram, take bending moment about this point, you get the value of x. You get the value of x. Do you understand at all? So what we are saying is that once you've sectioned, take shear force about the point you've sectioned, get the value of x. For this, take bending moment about the point you've sectioned, you get the location where point of contraflexion has occurred. So this is shear force and bending moment diagram.